All right. How exactly does humidity affect how long a virus can remain suspended in the air? Well, it's important to understand that humidity doesn't actually affect the virus directly. Rather, humidity affects the respiratory aerosol that carries the virus. This fundamental distinction is often overlooked. So then, the question then becomes, how does humidity affect respiratory aerosol? Well, this means that we are interested in the hygroscopicity of the aerosol. This is one of those weird science terms that simply means how much water does a chemical pull out of the air. When it comes to aerosol science, it's represented by a graph such as this. This is called a hygroscopic growth curve, and it describes how an aerosol changes size by picking up water at different relative humidities. The way you read this graph is as follows. Let's say you have a wad of respiratory fluid. Now, take away all of the water, which leaves you just a mixture of salts, proteins, sugars, and surfactants. If you were to make a 1 micron aerosol droplet of this mixture and then suspend it in air at 50% humidity, the diameter of this aerosol would be 1.1 microns. If you were to raise the humidity to 90%, the aerosol droplet would be 1.5 microns. And if you raise the humidity again to 95%, it would be 1.9 microns. Now, the utility of this curve is that this ratio is constant, meaning if you took a 2 micron aerosol droplet of water-free respiratory goo, an identical relationship would be seen. So at 95%, the aerosol droplet would be 3.8 microns. At 90%, it would be 3 microns. And at 50%, it would be 2.2 microns. All right, so the hygroscopic growth curve is really a useful tool that we can use to predict how respiratory aerosol changes size in different conditions. So then, how do we use this curve to estimate how long exhaled aerosol containing SARS-CoV-2 remains suspended in the air? To answer that, we first need to know the initial size of the exhaled aerosol. Now, during the pandemic, it was found early on that the majority of transmission came from asymptomatic people, meaning it was spread primarily through breathing and talking and not coughing or sneezing. Now, the aerosol produced through breathing and talking has a size distribution like this. Note that this is the size distribution at a relative humidity of 40%. So for the most part, all of the aerosol is under 4 microns. From the hygroscopic growth curve, we can then estimate that the largest dry size of the aerosol exhaled through talking and singing is about 3.8 microns, which is 4 microns at 40% our humidity. And when the humidity is increased to 70%, the aerosol would grow to about 4.6 microns, and at 90%, it would grow up to 5.7 microns. Based on the aerosol size and mass, we can estimate how long they remain suspended in the air. Now, this is an oversimplification in that this model prediction things like airflows generated by people moving are not considered, meaning that all of these values are going to be higher when people are present. No matter, we can use this as a baseline. From the estimate, we can see that the humidity has a moderate effect on how long the aerosol remains suspended in the air. Even in the most humid of conditions, the largest aerosol exhaled from talking will remain in the air for tens of minutes. And generally, most indoor air ranges between 40 and 70%, meaning that the shift in time the aerosol remains suspended in the air due to changes in humidity is mere minutes. And again, the values here are the largest exhaled aerosol from talking in perfectly still air. All of these values are going to go up dramatically for smaller aerosol, meaning that the humidity will only have a tangible effect on how long a fraction of the exhaled aerosol remains suspended in the air.